Hey there, and welcome to Raylene Math. Let's take a look at some vectors in the plane. Here we have vector A, which is 4, -3, meaning the horizontal position changes by 4 to the right, and the vertical position changes by going down 3. We can start a vector anywhere we like, but it's typical, if we don't have any other point to start at, that we could start at the origin. And so here we create a vector which lands in quadrant 4, and it has a horizontal component of 4 and a vertical component of -3, which we can write using these brackets, or we can use the standard vector notation with the I hats and the j hats to make it a little bit more algebra friendly, instead of having brackets and a comma separating the components. We can also come up with the polar components, which is to talk about the magnitude and the direction. The magnitude of the vector is the same as the hypotenuse of a right triangle that we create if we drop horizontal and vertical lines across. And so we have a base of 4 and a height, a distance of 3, and therefore using Pythagorean theorem we can come up with the magnitude of vector A written in this format of 4 squared plus -3 all squared under the square root. That's the square root of 25, which is +5. We can also see that we have a reference angle inside here to help us come up with the actual angle, which is a quadrant 4 angle. And so to come up with the reference angle, we know that the tangent of the reference angle is a positive ratio because a reference angle is acute. And so we have 3/4 for the opposite over adjacent, and therefore theta reference is tangent inverse or arctangent of 3/4. And so if we want to place that angle in quadrant 4, we have to subtract it from 2 pi radians or 360 degrees. So we have that the actual angle in quadrant 4 is 2 pi minus tan inverse of 3/4. We can do the same thing then with vector B. Vector B is going 8 spaces to the left and 1 space up, and we don't have to start it at the origin, it's just convenient if we do. But I'm going to place it over here so it's not too busy. And from here I'm going to imagine a new XY coordinate system or a new origin. My new origin would be at the tail of the vector, and I can see that this vector is in quadrant 2. So I have a right triangle again, and I can come up with the hypotenuse of that right triangle using the Pythagorean theorem. So first of all I'm going to write my vector B using the rectangular bracket notation and then using the standard vector notation. And then to come up with the magnitude, I'm going to use the Pythagorean theorem. So I'm going to get the square root of -8 all squared plus 1 squared, which is the square root of 65. And I'm going to get an angle in quadrant 2, which will be pi radians minus the reference angle. And the reference angle is going to be tan inverse of the opposite distance over the adjacent distance. And the opposite distance is 1, and the adjacent distance is 8. So it'll be the tan inverse of 1/8 for the reference angle, and we can approximate these to get a more meaningful number, but we have exactly the square root of 65 for the magnitude, and the pi minus the tan inverse of 1/8 gives us the direction in radians for the red vector. Now that doesn't change even if we move the red vector to the origin. We could do that. We'd still have the same magnitude and the same direction. In part B, we're asked to write a vector in standard vector form that is in the same direction as A, but has a length of 1. So we're not really trying to change the angle of vector A, which we found out was 2 pi minus the tan inverse of 3/4. But we do want to change the magnitude, which was 5. And so what we want to do is make the magnitude a little bit smaller. We want to come up with a vector with a magnitude 1 instead. So that sounds like we are resizing or scaling, and we want to make the vector a little bit smaller than it was. So we take the vector from before, which is not actually the same vector because we have a different sized grid. So I'm just going to stretch it until it reaches 4, -3, starting at 0, 0. And now we actually need to do the same thing, but in reverse. We need to make this a smaller vector keeping the same direction such that the length of it will be 1. So I'm actually going to draw a new one in red. And use this red vector. See if we can come up with 5 of them that all together land on top of the blue vector. And so here it looks like we've done a pretty good job of estimating a fifth of the actual vector. And so one of these red vectors by itself is the vector that we want. So this is our vector of length 1 pointing in the same direction as the blue one. And since it's a unit vector, we are going to use the same notation for a unit vector with a hat on top. So our vector A hat is the unit vector in the same direction as vector A. In part C, we want to sketch the sum of vector A and B, and we want to express that vector in standard vector form and in polar vector form. So we are going to take vector A. We can start it anywhere we want, and again we'll start it at the origin. And then vector B, we want to start it at the head of vector A. And so when we do this, we see that really the vector addition is really a sequence of steps or instructions about how to translate from one point to another to a final point. And so the resultant vector C, let's actually call that vector C, is going to be the sum or the net or the resultant of adding A and B. And so vector A goes 4 spaces to the right, but vector B goes 8 spaces to the left. So the net resultant for vector C is going 4 spaces to the left. Meanwhile, A is going 3 spaces down, and B is going 1 space up. So vector C in the end looks like it's going 2 spaces down. And so we can draw our resultant vector C as the sum or the resultant of going from point A, actually let's call it point P, to point Q, and then finally to point R. So vector C is like going from P to R directly without looking at point Q. And we can see that vector A was 4i hat minus 3j hat, and vector B is negative 8i hat plus j hat, and therefore vector C is equal to negative 4i hat minus 2j hat, which we can confirm if we go 1, 2, 3, 4 to the left and 2 down. So here we have vector C in standard vector form, and to get the polar vector form, we are looking for the magnitude and the direction. The magnitude, if you recall, is just the hypotenuse, and we can use Pythagorean theorem to get the magnitude of vector C. And so we get the square root of negative 4 all squared plus negative 2 all squared, which is the square root of 20, or 2 times the square root of 5. Meanwhile, the angle that we are looking for in standard position is going to be a quadrant 3 sized angle, but we can first focus on getting the reference angle, which is inside here between the negative x-axis and vector C. And so we are going to come up with the reference angle for vector C. So theta reference is going to be the tan inverse of the base, the opposite distance over the base distance, which is going to be 2 over 4, which is tan inverse of 1/2. And then to place the angle in quadrant 3, we need to add that reference angle to pi radians. And so we can write vector C with its magnitude of 2 times the square root of 5 and its angle of pi plus tan inverse of 1/2. We're going to do something similar here in part D. We're going to start off with our vector A, but then we want to add to it the negative B vector. So if we just write that we have vector D is equal to A plus negative B vector, we have to change B to its negative, which means we have to perform a 180-degree rotation about the tail, or we have to change both the x and the y components, the horizontal and vertical components. So vector B, if we recall, is equal to negative 8i hat plus j hat. Therefore, negative vector B will be positive 8i hat minus j hat. And we can do that by, let's see here, I think we can flip it. We can flip it twice, which is equivalent to rotating it 180 degrees. So now the vector B is going, negative B is going 8 to the right and 1 down. And so we can now move that to the head of vector A, but we're off the page, off the grid, so we can back those to any point we want to start at so that it gives us lots of room for counting. And so if we do that, we see that the resultant of A plus negative vector B is going to be this other vector that goes from point P to point R directly in one step. Of course, there was a point Q intermediate. And so if we use this picture, we can come up with vector A minus B. And so if we call vector D A minus B, we have 4i hat minus 3j hat minus B is a positive 8i hat minus j hat for a total of 12i hat minus 4j hat, which indicates that we've gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to the right, and 1, 2, 3, 4 down, which we have done for vector D. And then we want to come up with the magnitude and the direction. So the magnitude we find using Pythagorean theorem. And recall that the magnitude of the vector is nothing more than the hypotenuse of a right triangle. We can see here with the purple hypotenuse that we've created a right triangle for vector C, or rather for vector D, with a height of 4, a base of 12, and we can come up with the magnitude. So we're going to get the square root of 144 plus 16, which is the square root of 160, which is 4 times 4 times 10, so it's 4 times the square root of 10. Meanwhile, the angle that we want, if we imagine a new origin here, the vector for vector D now is in quadrant, the angle for vector D is in quadrant 4, and so we are going to have an angle of 2 pi minus the reference angle. And the reference angle we will find, because we have a right triangle, we have an opposite of the reference angle of 4 and an adjacent of 12. So we know that the reference angle will be found using a tangent relationship. Tangent of theta reference is the opposite 4 over the adjacent of 12, which is equal to 1/3, and therefore theta reference is going to be tan inverse of 1/3. And so there we have vector D has a magnitude of 4 times the square root of 10 and an angle of 2 pi minus tan inverse of 1/3 to give us the polar form of the vector. In the last example, we have part E. We want to come up with a vector 5 times vector A plus 2 times vector B. So we're going to take vector A and we are going to scale it, making it 5 times longer. And I'm going to do that by literally taking 5 of the same vector and lining them up to make a vector which is 5 times as long. And I'm going to group all of these vectors together and come up with vector 5a. I'm going to do the same thing for the red vector, except I'm only going to take 2 of them to create the vector 2b. And when I group those together, that creates a new vector. And then I'm going to add the red vector of 5a, the blue vector of 5a and the red vector of 2b. And when I do this, I realize that my vector, the resultant, falls off the grid. So taking advantage of the fact that I can translate the vector anywhere I want, I'm going to come back a little bit. And so I might need a little help with the algebra to know exactly where my final point is supposed to be. So I'll just leave that and then come up with the algebra for vector E. Vector E is going to be 5 times my vector A plus 2 times the vector B, giving us a total of 20i hat minus 15j hat, which is what we were doing for the blue vector, going 20 to the right and 15 down. And then for the red vector, we are going 16 left and then 2 up. And when we combine the like components, 20 minus 16 gives 4i hat, and negative 15j hat plus 2j hat is negative 13j hat. Well, if we take a look here, we go 1, 2, 3, 4 to the right, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 down. And so we see that if we take a point P, we go to a point Q, we end up at this point R, we're a little bit off, and this is going to be the resultant vector from P to R. The last step involved is to get the polar components of vector E, which is from P to R. You can imagine again that we have a right triangle here, and that the purple vector forms the hypotenuse of that. We can also imagine translating the purple vector to start at the origin, and so we see that the purple vector lies in quadrant 4. And so by using Pythagorean theorem, we get the magnitude of vector E to be the square root of 185. We get the reference angle for vector E to be tan inverse of the absolute value of the vertical component divided by the horizontal component. And to place the vector in quadrant 4, we have 2 pi minus the reference angle. And the reference angle is actually tan inverse of positive 13/4. And so therefore we have vector E to be a magnitude of the square root of 185 at a direction of 2 pi minus tan inverse of 13/4 radians. That's all for now. Thanks for checking out Raylene Math.